Okay, Unit 9, Application of Thermodynamics. We are now on question 46. Let's get to the question. Here we go. Sample before heating. Look, it was a solid. Now it's starting to let some particles roam freely. It's like a gas and a liquid. But this one, whoa, lots of particles. Okay, so these are, I want you to say, think of these as grandparents, right? Bunch of solids becoming grandkids, yeah? And now basically a lot of grandkids, okay? So the particle diagrams above represent a change in the physical state that occurred after heating two separate solid samples of a diatomic element. Which of the following best compares the relative magnitude of delta S and the entropy undergone by each sample? Both of them have increased in entropy, increased in disorder, because there's more grandkids involved. So the entropy values for both samples are positive. That is true. So you can get rid of B, you can get rid of D. Okay. The entropy values of both samples are positive, and delta S sample is equal to delta S sample 2 and sample 1. No way. No way. Look at how this one just got crazy. Okay, it went solid to like bunch of gases. This is like only a few gases. So sample 2 is way bigger than sample 1. The correct answer is C, and we're pretty confident about that one. Number 47. Galvanic cell. If this is a galvanic cell, then we are talking a positive E cell, a negative delta G. You know, it is thermodynamically favorable, all that kind of stuff. Okay, cell potential for the standard galvanic show above is 1.56. Okay, and they replace Ag with PbNO3. Okay, good. Which of the following describes what happens to the operation of the E cell and why? So, okay. Okay, the first one is Zn and Ag, and if you do the Zn and Ag, you could either do, remember, E cell is equal to E cat minus E an, okay? Cathode minus anode. Now, I don't know which one's the cathode, I don't know which one's the anode, but it could either be, if you're dealing with the Zn and the Ag, it could either be 0.80 minus negative 0.76 or negative 0.76 minus 0.80. Here's a problem. If you do the second one, you will get a negative E. If you have a negative E, that means you are not spontaneous. That means you're an electrolytic cell. This is a galvanic cell. So we know just by default, just by looking at these two numbers, this one is the galvanic cell, because that will give you a positive number, and the positive number will be 1.56, by the way, volts. Okay, so I know that that's where they got that from, okay? That Ag was a cathode, E was the anode, okay? Now, you're going to replace the cathode with Pb, and we see what Pb does. So let's see what we do here. We're going to change it with negative 0.13, and then it's going to be minus negative 0.76, right? Because you didn't change the other one, okay? Which would make it positive, gosh, I don't know, 89? Oh shoot, what the heck am I doing? It would make it, I gotta subtract that, 63, positive 0.63. Or maybe I'm wrong. Maybe it goes negative 0.76 minus negative 0.13, right? It could be the other way. And then in this case, this would become negative 0.63. So it's one or the other. Now, I would assume that because this, when you do this, this is true because the E cell that's the spontaneous reaction. This is the non-spontaneous reaction, right? So I believe you can say this with confidence that this is wrong. Okay, this is not what happened. This is what happened. Okay, when you changed out Pb. Okay, but when you changed out Pb, your voltage went down. Yes, so the answer is C. The cell potential decreases, right? The E cell went from 1.56 with Ag to 0.63. Even if you chose that one, obviously it decreases either way. So the cell potential decreases because the reduction of Pb2 plus is less thermodynamically favorable than the reduction of Ag plus. Yeah, so if your E cell is smaller, then you are less thermodynamically favorable, because if your E cell is less positive, you will be less negative of a delta G. So the answer, yes, is C. That's good. That's good. I like that question. Really cool. All right, let's move on. We're on number 48. All right. Based on the reduction potentials given in the table above, which of the following gives the balanced chemical equation the correct standard potential for the galvanic? Okay, again, I don't know. But I know that a galvanic cell is a delta H that is negative. That means its E cell is positive. So I'm either going to have negative 2.08 minus negative 1.18, or I'm going to go negative 1.18 minus negative 2.08, one or the other. But I look at this number right here, that's going to end up in a negative number, right? So since this ends up in a negative number, no, this can't be it. This has to be it here. So this means this was my E cat minus my E an. Yeah? So my Mn needs to reduce, which it is doing already. It is gaining electron. It is reducing. It is rigging. But this one needs to be flipped. All right? So I need my Sc3 plus. I can't have my Sc3 3 plus on this side. I have to have it on the other side, which it is. Now, notice that they multiplied it by 2 and 3. Why did they multiply by 2 and 3? Because they had to get these electrons to cancel out with one another. So they multiplied this by 3, they multiplied this by 2. But that's not the defining factor, because they both have 2, 3, 2, 3, 2, 3. Like that's not what they're actually trying to figure out. They're trying to figure out, did you get the correct E cell value? So this is the correct E cell value. I would bet my money that D is the correct answer, because that does look like it'd be 90. 0.62 is just not enough. Okay, and that also helps us because, look, we knew the E cell had to be positive because it said it was a galvanic cell. If an E cell is positive, then your galvanic cell is negative, or your delta G is negative. 49, you have strontium plus fluorine yielding strontium fluoride. Okay. And the equilibrium constant of the reaction represented above has a value of 1.3. So equilibrium constant, we know what that is. That is a K. Your K is above 1. That means you have more product and less reactant. Okay. And at 50 degrees Celsius, the value of constant is less than 3.1. So what happened? At 50 degrees Celsius, more reactant came into play. Maybe not that much, but more. Based on this information, which much of the following must be correct? So I want you to bring you back to equilibrium. Heat must have been a product. If heat was a product and we increase temperature, your Le Chatelier seesaw goes like this, yes? If your heat was a product, your heat increasing, your temperature increasing would have made it go this way, and then what would have happened? You would have gone back. You would have created more reactants. Created more reactants. So I bet heat was a product. I bet this was exothermic. The answer, E. Delta H for the reaction is negative. In other words, exothermic. All right, number 50. All right. At 1 atm, a sample of ice is heated to liquid water and then to water vapor. The heating curve is shown in the graph above. Which of the following lists the signs for the changes in enthalpy and entropy for the process corresponding to the segment X going from left to right? What's happening as we go left to right? What's happening? We are the liquid water is starting to absorb energy. It's absorbing. Oh, what the heck? If it's absorbing energy, then what's it going through? It's endothermic. It's accepting energy, so it has to be the delta H is positive. So we can cancel out this, we can cancel out this. Okay, the delta H is positive. Now, what's happening to the entropy as you go left to right? You're gaining entropy, you're becoming a gas. You're starting to get more disorder. So the correct answer is B. Okay? Just think about what's happening left to right. And look at the label on the x-axis. The label on the x-axis says heat is being absorbed. All right, let's look at number 51. Number 51, here we have, oh, this is, I don't know why this question's here, but accidentally here. Let's go over it. It's a good review. The ionization energies of the unknown element X are listed in the table above. Which of the following is most likely the empirical formula of a compound from the element X and the phosphorus? Look at the ionization energies. Do you see that it goes through, boom, like a big jump? Like, yeah, you're going to say that's 8,000 to 10,000 is a big jump too, but 1,000 to 8,000 is a big jump. Okay, that's a really big jump. So its loss of its third electron is a big deal. Look, let's just start with neon. Let's say we were dealing with neon. If we were dealing with neon, it's the big, neon does not want to lose an electron, yes? The first electron loss would be the jump, okay? What's after neon? Lost my mind for a second. It's sodium. Sodium, it doesn't mind losing its first, but it really, then it becomes neon, but it really minds losing its second when it's no longer a noble gas, right? It doesn't have a noble gas configuration. What's after sodium is magnesium. Magnesium doesn't care about losing its first. It really doesn't care about losing its second. But now that it's lost its second, it became a noble gas. It really doesn't want to lose its third. So who had the big jump at third? Yeah, magnesium. Magnesium didn't want to lose its third electron. This must be something in the same column as magnesium. And what's magnesium's charge? It's a 2+. We know phosphorus is a 3-, so this would crisscross, and you would get C is the correct answer. That's old school, man. That's 1s2, 2s2. Remember those days when it was really easy? All right, let's go to 52. We have a half reaction between magnesium and chromium. Okay. Based on the information in the table above, which of the following shows the cell potential energy of the Gibbs free energy overall reaction that occurs in standard galvanic cell? Galvanic cell. Delta G must be negative, therefore E cell must be positive. Okay, so you're going to get one of two choices. You can either go negative 2.37 minus negative 0.74, or you're going to get negative 0.74 minus negative 2.37. And I'm just going to tell you right now, this sucker right here is going to be positive. And you can just see it. Like this number up here, that's going to be a negative number. That means your E cell would be negative. That means your delta G would not be galvanic. Your delta G would not be spontaneous. So the bottom one has to be true. So your E cell is equal to E cat minus E an. So in other words, our chromium needs to rig. It needs to gain an electron. However, our magnesium needs to oil. It needs to be the anode. So this needs to flip. Okay, so I don't want to write it out, but okay, I will. Cr3 plus 3 electrons plus magnesium. Remember, magnesium, the top equation flipped. Then those are going to become magnesium 2 plus 2 electrons plus Cr. So these are the two. Now, notice I flipped the top one and I added them together. Now, the electrons need to cancel out. So I need to multiply this guy by 2, and I need to multiply this guy by 3. So this is going to go 2, 6, 3, 3, 6, 2. And your electrons are going to cancel out, right? All right. All right. Now I can do my, now I got to find out what my Gibbs free energy change is. So my delta G is equal to negative NFE. Look, this is going to be, you have to estimate here. Okay, what is the N? And this is the first time we've ever had to solve for Gibbs free energy with this equation. Your N is moles. Moles of what? Moles of your electron. So you have 6 moles of electrons on both sides. That's when when they canceled out. Okay, that's why you have to do that balancing act. Okay, your Faraday's constant. Okay, 96,500. Your E cell is, I don't know, 1.63. Okay, I don't like dealing with any of these numbers. These numbers are ridiculous. So, do I have to do it? No. Okay, I also want you to remember your Faraday's constant is in joules. So I'm gonna change it to kilojoules by doing that. Boop. Okay, I made that in kilojoules because your delta G has to be in kilojoules. So let's just change these numbers. Can I make it 6 times 100 times 1.5? And that's 900, or it's negative 900. That's good estimation right there, buddy. That means the answer is B. Okay. By the way, yeah, I mean, we already found out the E cell was 1.63, but that's the nail in the coffin right there. Okay. All right. Estimation. All right. The equation above represents a decomposition of a compound XY2. The diagram shows 2 reaction profiles, path 1, path 2, for the decomposition of XY2. Okay, path 1, path 2. The reaction is thermodynamically favorable under standard conditions at 298 K. Therefore, the value of delta S must be. Okay. Well, I'm going to tell you this. Looking at that, it looks like it increased in enthalpy, right? Like, it increased, well, it didn't increase in enthalpy. You see the enthalpy change here was 50. It was positive 50. But it also probably increased in entropy as well. No. We just don't know what that thing became. Yeah. Okay. The delta S increased as well. I mean, I wish they told us which substances these were, but like, let's just assume this is one thing and it became 2 things. So your delta S is positive. So, okay, so your delta G is equal to delta H minus T delta S, okay? Now, these 2 things are both positive, yes? And the thing is that this makes temperature dependent on it. But think about it. You want, at this point, like once you know that for this to be thermodynamically favorable, enthalpy is hurting you, okay? So you want T delta S, okay? You want T delta S to be greater than delta H, okay? Then it will be entropy driven, causing this to be negative. Okay. Now look at look at your possible answers. Okay, you see that 298? That's the temperature. So what do they do? Delta H divided by 298, is less than delta S. So in other words, delta has to be greater than delta H 298. The answer, C. That's a really cool way of doing it. That was just cool. Just cool. All right. The decomposition of H2O is represented by the equation above. A student monitored the decomposition of 1 liter sample of H2O2 at a constant temperature of 300 K and recorded the concentration of H2O2 as a function of time. The results are given in the table below. So what do we know? This is happening, okay? The reaction is thermodynamically favorable. It tells us it is thermodynamically favorable, so this must be negative. Delta S, you have 2 aqueous things becoming 2 liquid things and a gas. Ooh, the gas came out of nowhere. That's increasing in entropy because gases are nuts. They make you add disorder. So delta G is negative, delta S is positive. Negative, positive, negative, positive. What is going on here? The correct answer is B, I bet. But you see how they messed up? That's supposed to say delta S. Typo. Okay, all right. 55. Okay, this is a series of questions that is seriously, okay, interesting. So freaking interesting. All right, let's not start on this one. All right. No, okay. We'll start on this one. This one might be the hardest one of them all, but okay, let's get this through our head. Number 55. All right. So you have a spontaneous reaction that occurs when the cell above operates. Ag plus CD. Okay, Ag plus becoming Ag right here. That is showing that it is gaining electrons because it's going from neutral to no charge. So it is gaining electrons. This is the rig. That means, that means Ag is our cathode. This is where we are rigging. So electrons are coming this way. That means CD is our oil. That means electrons are leaving this way. That means that CD is slowly disappearing and that Ag is slowly getting bigger and bigger, okay? So that's what's going to happen, okay? The spontaneous reaction that occurs when the cell above, which above occurs in the following circumstances. A 50 milliliter sample of a 2 molar CdNO3 solution is added to the left beaker. Okay, so we're going to add more CD to this, okay? And you could actually calculate how much more it got added, but look, it was a 1 molar solution, and now we're adding 2 molar solution. The concentration is going to increase, okay? So the concentration of CD and the moles of CD2 plus are going to increase. And guess what CD2 plus is? Well, look at your reaction. Let's write out the reaction so you can see it, and I can do it on a Le Chatelier thing. Ooh, okay. If I'm going to be a good boy, make this AQ, make this solid. And look, both of those things are not strong ions, right? So you're going to have your CD2 plus AQ and your AG solid, yes? Now, if you put this on a Le Chatelier, yeah, seesaw, if we added more CdNO3, guess what happens to it? CD is a product. You see that? Since CD is a product, it gets lighter on the right side. Since it gets heavier on the right side. What will it do to get back to equilibrium? It will create more Ag and more CD. It will create more reactant. Okay? So think about this. Remember, your delta G is equal to negative NFE. And your delta G is also equal to negative RT ln K. And we've already said that negative NF and negative RT are all just, that's just a negative number and a negative number. So really it just comes down to your E is equal to your ln K. Well, okay, bear with me. It's an ln Q because we just stressed the system by adding more CD2 plus into it, okay? So as we added more CD2 plus into it, what will it do to get back to equilibrium? It will create more reactant. If it creates more reactant, what happens to K? K goes down because we're creating more reactant, right? We're going this way and creating more reactant. If we're creating more reactant, then K decreases. If K decreases, your ln decreases, or your ln K decreases. If your ln K decreases, your E decreases. So the answer here is that the voltage decreases, but it remains above 0. It's not going to go to 0. That would mean that, that would mean that it completely stopped. It didn't stop. It just remained 0. So this is when we are incorporating the concept of delta G in thermodynamics of electrochem and equilibrium at the same time. Super interesting question. Okay. 56. The spontaneous reaction that occurs when a cell operates there. Which above occurs for the following circumstances? The silver electrode is made larger. You know, if we made the silver electrode larger, let's go back to the equilibrium. You know what that is? It's a solid. It doesn't play in equilibrium. It doesn't affect equilibrium. If it doesn't affect equilibrium, it doesn't affect the E cell. So if you made the silver electrode larger, no change in voltage. Doesn't work. Doesn't do anything. All right, 57. The spontaneous reaction that occurs when the cell operates, which of the above occurs for the following circumstance? The salt bridge is replaced by a platinum wire. Okay, the reason why the salt bridge is important is because there are Na pluses and let's say NO3 minuses. And I'm not saying that there are those things. There's just ions in here. And as the Ag is increasing, this solution is becoming less positive. So all of a sudden, these NAs want to go that way. Okay? And then that means the NO3 minuses want to go that way. Okay? Without the salt bridge, the galvanic cell doesn't work because it allows the electrons to pass through while keeping the current flowing. Okay? So if you change the salt bridge out and you replace it with the platinum wire, the platinum conduct electricity, but it cannot share positive and negative ions with opposite sides of it. So the voltage becomes zero and remains zero. It's basically like you turned it off. Okay, your salt bridge has to have a positive ion and a negative ion for this to work. Okay, 58. Spontaneous reaction occurs when the cell operates this. The current is allowed to flow for 5 minutes. Look, if the current is allowed to flow for 5 minutes, the reactants are going to start getting taken up, right? Like you're going to start losing. You're going to start losing CD. CD is going to get less and less. Ag is going to get more and more consumed. It's just going to overall. When you do this, your voltage is going to ultimately just decrease. Now, it's not going to get to zero because you're not done yet, but you're just going along in the reaction. It's going over and over and over and over again. The voltage will decrease, but it won't go to zero. All right, that was a cool set of questions. This set of questions really shows how they want you to think of delta G as something that can go in between electrochem and equilibrium and kind of be able to manipulate the formulas that way. All right, let's look at 59. You have an animeter. This is a galvanic cell again. Okay, it has to be positive. The E cell has to be positive. The delta G has to be negative. How do I know that? Because there's a salt bridge. All right. A vanadium-lead galvanic cell. Ooh, it just told me a galvanic cell. In the diagram above, initially operates under standard conditions. According to the net reaction shown, which of the following mathematical relationships would be most useful in determining the change in mass? Ooh, shoot. Volts, electrons after 1 minute of the operation without... Okay, the answer, this is B. I'm not going to get into this, okay? Look, this is a Nernst equation. We don't teach that anymore. This has something to do with equilibrium. Obviously, this is with your E cell. This is your spontaneity and your therm chem. This is the last IVR type question, and I just don't want to do IVR type questions. But the answer is B. Okay, last one, number 60. Okay, number 60, you have HA, H2O, A minus, H3O plus. When I see HA, are you guys like me? Do you guys see weak acid there? Yeah, buddy. All right, the delta G is positive, meaning this is not spontaneous. Based on the chemical equation and delta G given above, which of the following justifies the claim that HA is a weak acid? Everything? Okay, all of these say delta G is positive, like delta G is above zero, and that's true. So if delta G is above zero, that means Ka is less than 1. Right? So it can't be A or B. Ka has to be less than 1 because, look, if your reaction is not thermodynamically favorable, if your reaction is not spontaneous, then you don't produce a lot of product, you have a lot of reactants. So it's either C or D at this point. And, okay, if D was true, if HA didn't dissociate, it's not a weak acid. A weak acid partially dissociates. So the correct answer is C. Okay.